Building quadratic models from verbal descriptions and from data. So in the previous section, we solved word problem applications of quadratic functions. We found maxima and minima of functions by finding the vertex of those quadratic functions. In this section, we're actually going to come up with the functions. So we have to use the word problem, use the given information to come up with the function ourselves, and then from there it's similar to the last section where we're finding maxima and minima, finding the vertex of the parabolas. Okay, so first, a common application of quadratic functions is revenue. So revenue, the money received from a sale of a product. So our equation for revenue, revenue is x, the product of x and p. So revenue, the money received from a sale, is the product of x, the number of units sold, and P, the unit selling price, so the price per unit. So when you solve these problems in this section, they're going to expect that you know that R equals XP function, that R equals XP equation. Okay, so our first example. The marketing department at Texas Instruments has found that when certain calculators are sold at a price of P dollars per unit, the number X of calculators sold is given by the demand equation, X equals 21,000 minus 150 P. So this is the demand function. Now in part A, we want to find a model that expresses the revenue as a function of the price. So first of all, revenue as a function of price. That means we're looking for an R of P. So we want to find R of P. So that means we want to find a revenue equation that only has the variable P in it. So we're going to start with our R equals XP, and this is not a function of price because it has that X in there. So we're going to need to substitute in for that X, but we were just given right here that X as a function of P. So we can substitute this in here for X. So then that will give us an R of P. So that will be 21,000 minus 150p times p. So we multiply that out, 21,000p minus 150p squared. And you may want to rewrite that in descending order, negative 150p squared plus 21,000p. Either way is fine, but it might be useful to keep it in descending order for later when we find the vertex. So here's our R of P function. So similar to section 3.6, you have to know an equation. They expect that you know the revenue equation, and then they're giving you a piece to substitute into that equation and then make your function. Okay, part B, we want to find the domain of this revenue function. So as we've talked about, in a lot of word problem applications, in real life examples, real life quantities frequently are positive. So in this case, our domain, our P values, represent the unit selling price. So we know that has to be positive. So we know that P has to be greater than 0. And then we also know, that revenue is the product of the unit selling price, P, and X, which is that number of units sold. So up here, we have our product of units sold and our price. So we know that this also has to be positive. So the two quantities that are involved in revenue, units sold and price, both have to be positive. So if I set my 21,000 minus 150p, that has to be greater than or equal to 0. So technically you could sell 0 units, although that obviously wouldn't be ideal. So 21,000 minus 150p is greater than or equal to 0. So if we solve this inequality, if we add 150p to both sides, we get 21,000 greater than or equal to 150p. Divide both sides by 150, and we should get 140 here. So if I turn this around, so that my P is on the left side, because we typically read left to right, so P is less than or equal to 140. So for our domain, We know that that price has to be greater than 0, can't have a negative price. And then here, because the unit sold has to be greater than or equal to 0, here's another constraint, another restriction on our domain. So if we put the p greater than 0 and less than or equal to 40 together, we can make a chain. So that means p has to be between 0 and 140, and not including the 0, but yes, including the 140. So this is our domain. And just pay attention whether they want it in interval notation or in an inequality form like this. Okay, so now we want to know what unit price should be charged. So unit price is P to maximize revenue. So maximize, that should sound like maximum. And since we're talking about a quadratic function, so our revenue function's quadratic, it's degree 2, p squared. So we know that maximum is going to occur at the vertex. We know that this parabola opens down because it has a negative coefficient of the squared term. So since the revenue function, so R is a parabola opening down, so that means the max is at the vertex. So we can just find the vertex. We can use our negative b over 2a to find the p-value of the vertex, which would give us the unit price. So just remember here, they want unit price. We're trying to find the p-value. P equals what? So we're going to fill in. So in our negative b over 2a. So in this case, this is why I had you guys write this in descending order up here so you don't get confused and actually accidentally mix up the a and the b. So here's our a, and here's our b. So if we fill in, we want the opposite of 21,000 over 2 times negative 150. So here's some mental math, you know, at all costs. I want to keep our brains fresh. So we know we've got a negative in the numerator and a negative in the denominator. Negative divided by negative will give us a positive. We know in the denominator 2 times 150, 2 times 15 is 30, add the 0 is 300, so this is 300. And then we've got 21,000 divided by 300. If we divide by 100, that's the same as crossing off 2 zeros in the numerator and denominator. So that gives us 210 divided by 3. Well, 21 divided by 3 is 7. Add your 0. And there's 70. So that means this is P. P is price, so that's $70 per unit. In this case, the unit of calculators. $70 per unit will give them the maximum revenue, the maximum money brought in per sale of these calculators. So that's the price. That's the p-value at the vertex. Now, in part D, we actually want to know that if we charge this price, what is the maximum revenue? So now we want the actual y value, or the r of p value, at that vertex. So we'll just fill in. We'll take r of 70. So we'll have negative 150 times 70 squared plus 21,000 times 70. So we can enter that into the calculator, and we should get 735,000. So that means if we charge $70 per unit, we will bring in the maximum amount of money. The maximum revenue will be actually $735,000. So in part C, they were asking for the price, the P. In part D, they were asking for the R, the actual revenue. And that would be the 735,000. Okay, then part E, they want to know, in order to bring in this maximum revenue, how many will they actually have to sell? Well, remember, we were given this demand function up here, so the units sold as a function of the price. So we can fill in x equals 21,000 minus 150 times, and we know that the unit price of $70 will bring us that maximum revenue, so we'll plug in the 70. And this will give us 10,000. Oops. This will give us 10,500 units. So in part E, they wanted an x value. So we actually had several variables in this function, in this problem. So in part E, if they sell 10,500 units, that will bring in the maximum revenue of $735,000. Okay, now, so if we want to graph our function, go to our calculator here. I've entered the function into the calculator, so the 21,000x minus 150x squared, or again, vice versa, we had it flipped here in descending order. Either way, it's good. Now, as far as our window, we actually know a lot more information in this problem. We already found the domain, so we know the domain of this function was between 0 and 140, so I made my x min 0 and my x max 140. And then since I increased, that's a relatively larger window, larger than the standard negative 10 to 10, so I increased the scale. And remember, there's never just one right way, one correct window, just a little trial and error. You can always make your window larger or smaller. Then for our y value, our y value is the R, the revenue. So we know revenue has to be greater than 0. So we start at 0. And then we actually found the maximum revenue was $735,000. So we know it can't go any higher than that. So I actually went just slightly higher just so that we could get a better picture. So if you know it goes up to $735,000, it's not a bad idea to go a little bit higher just so you can get a better view of the shape. And then again, we drastically increased the window there from our standard negative 10 to 10, so I increased the scale here to 100,000. Again, just one example of a window that will allow you to see the good shape of this. So if we go to our graph, we can see our parabola opening down as we would expect. So we can calculate our vertex here, and we would expect that our vertex is going to occur with an x value, or a p value, of 70, and a y value, or r value, of 735,000. So let's check it here. Second, trace to calculate the max, option 4. So we can move our cursor a little bit to the left of where that vertex appears, and hit enter. Move it a little bit to the right. And hit enter, and hit enter one more time, and we can see that we do get 69.9999999, and that's 70, and then 735,000 for our y value. So let's make a little sketch in our notes here so we have this to take away to study later. So if we make our axes, we've got this parabola opening down, again just the ballpark of the shape, and we found this vertex algebraically, and we've checked it on the graphing calculator, 735,000. So this is our P and our R of P axes. And then if you guys want to make a note of the viewing window that you use, so if you go back in your notes, you can reproduce this on the calculator. Remember, we did an x min of 0, an x max of 140, and we increased the scale to 10. And then our y min was 0, our y max, 750,000, and our y scale, 100,000. Again, just an example of a window. There's certainly lots of other possibilities.